Hello again, AP Chem students. This is Lou Akampora from Advanced Kentucky, and I'm going to go over some electrochemistry today in this little review packet. So, electrochemistry will appear on the AP Chem exam and possibly several problems. Students have a hard time with it traditionally, but let's get back to some fundamental concepts and see how we can make this a little bit more logical. So I want to tie this to oxidation reduction reactions, and a simple oxidation reduction reaction or redox reaction would involve the transfer of electrons from one species to another. And you may have done something like this, but imagine you had a beaker or a test tube with some silver ion, some dissolved silver ion, possibly silver nitrate solution. So let's see if we got some silver ion in water, and we drop in a piece of metallic zinc. Some of you may have done a reaction like this. This is a single replacement reaction, but it's also a redox reaction, and you would see some changes happening. You would see little bits of metallic silver forming on the zinc, and possibly they would settle to the bottom of the beaker, depending on the concentration of the silver ion solution and how much there are. The zinc metal would be corroded and would dissolve or appear to react, and we would see that a reaction would certainly occur. The beaker, the solution would get a little bit warmer. This is going to be an exothermic reaction, and we'd be able to write a balanced equation where the reactants are zinc atoms and silver ions, and the products are going to be silver atoms and zinc ions, and we want to be a little bit careful here because zinc ions have a charge of +2, silver ions have a charge of +1, and zinc atoms and silver atoms are, of course, uncharged. So we need to be careful about balancing. While this equation is balanced in terms of mass, it's not quite balanced in terms of charge. If we look at this, the zinc atoms each lose 2 electrons to become a zinc ion. Silver ions each gain 1 electron or are reduced to become a silver atom. So we need 2 silver ions becoming 2 silver atoms for each zinc atom that loses electrons. And this is our net ionic equation for the reaction that happens. You could have predicted that, or you should be able to predict that, given a table of standard reduction potentials, and we'll see here, and certainly you would not be called upon to memorize these values, or even these half reactions. These are given to you. Don't spend your time memorizing this when there's so much more important things to be memorized. But if we look at this, notice that these are written as reduction half reactions. Now, I suspect there's a lot of confusion about what makes each of these a half reaction. And what makes it a half reaction is that each of them explicitly includes electrons. So electrons are explicitly in each of these balanced half reactions. In fact, these are all reduction half reactions. These are conventionally written so that some species could be a silver ion, could be an oxygen molecule in the presence of hydrogen ions, but some number of electrons are being gained, so these are all written as reductions to produce some species on the right-hand side of the arrow. These are all balanced, and you can confirm for yourself that each of these half reactions is in fact balanced, but they explicitly include electrons, which means they cannot happen in isolation. Electrons will never appear in an overall balanced equation, so if some species is gaining electrons, then somewhere something else has got to be losing electrons. And the trick, and we'll see this a little bit later, in taking our half reactions and combining 2 of them into you guessed it, a full reaction, is to make sure you take and you flip one of them, turning that reduction into an oxidation. So in this case, it's pretty obvious from our reaction setup that the 2 half reactions that we are dealing with is this reaction of silver, the reduction of silver ion to silver atoms, and as written, the reduction of zinc ions to zinc atoms. These cannot both occur at the same time, so we've got to flip one, and pretty clearly we're going to flip this reaction and turn it into an oxidation. So we will have zinc atoms becoming zinc ions plus 2 electrons. And that would be the oxidation half reaction that occurs. We have silver ions plus 1 electron going to silver atoms. And now that I've written these two half reactions separately, be careful, this plus is the charge on the ion, and this plus just tells me we're adding the electron to the silver ion. The second thing in combining two half reactions to a complete overall reaction is to make sure the total number of electrons lost equals the total number of electrons gained. So we've got 2 electrons being lost here and 1 electron being gained. Clearly we need to multiply this entire second reaction equation by 2 and then combine, and when I get that, I get my zinc atoms plus 2 silver ions. I'll go ahead and include the 2 electrons from here. That's all of my reactants, and then my product will be a zinc ion, 2 electrons, and 2 silver atoms. And I better be able to cancel the electrons from both sides, since that's the whole reason I multiply by 2. And I'm left with my net ionic equation, which we had already figured out up here. A common question would be to ask for the cell potential for this reaction or for this cell, and that's going to be obtained from this table by the difference between the standard reduction potentials of our 2 half reactions. Some books and some teachers will have you change the sign of this one when you flip it and then add them. I prefer to just take the difference between those 2 values, in which case E naught, our standard cell potential, would be 0.80 volts minus negative 0.76 volts. And remember, we're going to subtract the difference between those numbers to get 1.56 volts. And that tells us, well, what is a volt? And it's related to energy, but it's not quite energy. And that really, I think, is the unfamiliarity that many students have, because electrochemistry deals with charge, and most AP chemistry students, I think, are very comfortable dealing with amount in terms of moles, and we could talk about moles of zinc or moles of silver ion, but we're not really familiar with using charge. And charge is measured in units called coulombs. This is really a historical accident. Remember that chemistry is a fairly young science, certainly compared to physics. John Dalton's atomic theory is really only a little bit more than 200 years old. And physicists have been measuring charge and dealing with charged particles for years before that. I'm sure that Greeks would rub a little piece of amber on a sheep or a wool and use it to pick up little bits of papyrus. And you know, of course, the story of Ben Franklin and the kite and the key and the lightning storm as he was trying to measure charge. Well, and that was the 1700s. So for a long time, chemists or bench chemists didn't really understand the role of charge in chemistry. When it was worked out, starting with Thomson's cathode ray tube experiment in 1897, physicists had already been measuring charge for centuries, and the unit of charge is a coulomb. It's not really very useful for us as a chemist to talk in terms of coulombs, but we have this historical basis. It turns out that the charge on one electron, the charge on an electron, is negative 1.6 times 10 to the negative 19th coulombs. Not a very practical number, but chemists don't usually deal in individual electrons. When we deal with particles, because our atoms and photons are so small, we usually deal in terms of a large number of particles, of those particles, and that number is, of course, Avogadro's number. So what we really would like to know is the charge on a mole of electron. We would get this by multiplying by Avogadro's number, and usually we'll lose the negative sign and call this Faraday's constant, which is 96,500 coulombs per mole of charge. So if you had a mole of electrons, the charge would be, on that would be 96,500 coulombs. If you had 1 mole of zinc, reacting with 2 moles of silver ions to form a mole of zinc ions and 2 moles of metallic silver, 2 moles of electrons would be transferred, and that would be twice 96,500, or 193,000 coulombs of charge, a fairly large number, but a coulomb's a much smaller unit than a mole in these terms. The volt, this unit in which we are expressing potentials, is equivalent to a joule per coulomb. So something you should know is that a volt is 1 joule per coulomb. So if this reaction happened, and let's say 1 mole of zinc metal reacted with 2 moles of silver ion to form 1 mole of zinc ion and 2 moles of silver metal, 193,000 coulombs of charge would be passed, and each one of those would release 1.56, we've already erased that number, but E cell 1.56 volts, or 1.56 joules per coulomb. So we would get from that reaction about 300,000 joules of energy, and we might say that the delta G is negative 300 kilojoules per mole. And if you think about it, that relationship, that the delta G of a reaction, or a redox reaction, is negative N times F times E naught, where N is the number of electrons transferred in the reaction. That's the number we crossed out down here. F is Faraday's constant, which is always going to be 96,500 coulombs per mole of electrons, and the cell potential is whatever the cell potential is from the table of standard reduction potentials. So it's this, we see in here both some stoichiometry in counting up the number of moles of reaction that occur given the number of moles of electrons that are transferred, and the thermodynamics in relating the delta G value to the cell potential. We talked about the volt as being a joule per coulomb. Well, let's see how we might get, before we talk about the other unit, let's see how we might reconfigure this, because if we had the piece of metallic zinc immersed in a silver ion solution, the energy would be released, but it would be released in a fairly unusable form as heat. It's great if you need to heat your house, but that wouldn't be a very practical way of doing that. We'd like to be able to release this energy and get useful work out of that. And to do that, we're going to turn the redox cell, or the redox reaction, into an electrochemical cell. So I might take, and if you have the notes you can follow along, I might take a beaker with some zinc sulfate or zinc nitrate or any solution that contains zinc ion, and if this is at standard concentrations, that would have a concentration of 1 mole per liter, and I might immerse into it a piece of metallic zinc. Nothing is going to happen. The zinc metal will not react with zinc ions, or they might react, but we wouldn't notice any change. So nothing will happen here. I would take a second beaker, and here I'd construct my other half cell, and in that I would take a solution of silver ion with an electrode of metallic silver. And again, nothing is going to happen here either. But these two reactions would have a tendency to happen. I don't want to say they would want to happen. That's a little bit too anthropomorphic for me. But there would certainly be an electrochemical potential for this to happen. And over here, we would see the zinc atoms would have a tendency to be oxidized to zinc ions, releasing 2 electrons. In this compartment, this half cell, this is a half cell because nothing would happen until you connect 2 of them, the silver ion would have a tendency to gain an electron to form a silver atom. Nothing will happen if these 2 cells are separated, but we would normally connect these 2 cells with some conducting wire, and I'll put a resistor in there, and then maybe a voltmeter across here, and maybe a little switch in here so I can connect it or not. And still nothing is going to happen, although we can see that now there are electrons that would be pushed through the wire. Remember, electrons will pass through a metal. A metallic wire is a good conductor of electricity. And think about your intermolecular forces and structure of matter. So electrons would be pushed this way through the wire, but nothing can happen, or at least they can't sustain a current, because when those electrons get over here, a negative charge will build up, leaving a positive charge in this electrode, but that negative charge would prevent the flow of additional electrons. In order to maintain a steady current, we would have to have a way to neutralize the electric charge, and that's conventionally done with a salt bridge. The salt bridge is just, in the textbooks, it'll look like this, but it could take various forms, a paste or a sponge that's soaked with an electrolyte, but there'll be positive ions and negative ions, and I'll make this sodium sulfate, since those ions are not reactive with anything that I've got in my beakers. And these ions in the aqueous solution will be able to migrate to neutralize a charge. So sodium ions would flow, or whatever positive ion is present would flow in the same direction as the electrons, and the negative ions would flow in the opposite direction. And we would see these ions flowing through the salt bridge to maintain and charge neutrality. At this point, we would measure a potential, and that potential would just be what we had earlier, 0.80 volts minus negative 0.76 volts, or 1.56 volts. And that's the thermodynamics of our reaction. The stoichiometry comes about because while it might be possible to measure the mass of zinc that is consumed or the mass of silver that is produced, and remember when we combine this equation, we need to multiply that by 2 to get our overall balance equation. The way we would normally do this in practice is to measure the charge that flows through our wire. And actually, we don't measure the charge directly, but we measure the current. So we would put an ammeter here, and this brings us to our second unit. An amp is a unit of electric current, equivalent to a coulomb per second. So what you would typically do is measure the current, and typical currents in a cell might range from 0.1 amps to maybe even 100 amps or more. Remember, a coulomb is not a very large amount of electrons. It's only 1/96,500 of a mole of electrons. So your car battery probably generates about 500 amps of current with no problem at all. But an amp is a coulomb per second, and that's something to know. So the charge transferred, the charge is going to be the current times the elapsed time. And for historical reasons, I is used for current and delta T for time. So if we were to pass a current of, let's say, 2 amps for 10 minutes, well, 2 amps times 10 minutes, we would want to write that as 600 seconds. And that means we would have transferred 1,200 coulombs of charge. That's the way a physicist would certainly like to express this, but as chemists, we are often more concerned with moles of things, and we divide that 1,200 coulombs by 96,500 coulombs per mole of electrons to get moles of electrons. And once you've done that, you are, I hope, on familiar ground, because you can use that moles of electrons to get a mole ratio using just the half reaction. So if I wanted to know how many moles of silver were formed, and I knew the moles of electrons transferred, it'd be a 1-to-1 mole ratio. The moles of zinc that was oxidized, remember this reaction is going to go that way for our cell, would be half the number of moles of electrons transferred, since there's a 1-to-2 mole ratio. So those are the fundamental principles of electrochemistry. It's just redox, where you've separated out the read from the ox, or the reduction from the oxidation, and causing those electrons to go through an external wire. So if you have the handout, there are a couple of practice problems for you, and this might be a good time to pause the video and try to answer these on your own. And then I'll just come back, and you can restart the video and we can work through these together. So let's pause right now. And welcome back. Though the first problem here is very similar to what we did. So we've already done question 1. Part A, we've already written the balance equation for the chemical reaction that occurs as a cell operates. We've shown the direction that electrons flow in the wire, and that is left to right, since I have the zinc half cell on the left here, as in the diagram. And the direction of, well, we have positive ions, but the positive ions, doesn't matter if they're potassium or sodium, they will flow left to right as the cell operates. And the ideal cell potential, we already have written on the board, is 1.56 volts. Let's go ahead and use the numbers here to get the stoichiometry. Let's assume that this cell operates. We now close this switch and allow a current to flow, and a constant current of 1.5 amps flows for 40 minutes. Important to remember that an amp is a coulomb per second. So we have, I think I'm going to not need this anymore for today. So 1.5 amps would be equivalent to 1.5 coulombs per second times, we could multiply by 40 minutes, but we absolutely need to convert that to seconds. I'll just do that in my step and then call out 2,400 seconds. Some of you can certainly write out an extra step there, and that gives us 3,600 coulombs of charge. Frequently on an AP Chem exam, you'll get 1 point just for that, and it's a fairly accessible point, I think, but you've got to know what an amp here and a coulomb is. The next thing, and frequently this won't be explicitly asked for, but you'll almost certainly need to know how many moles of electrons, and those are called Faradays, are passed through the cell, so that the moles of electrons would just be our charge in coulombs divided by 96,500 coulombs per mole of electrons. And excuse me for a moment. I'm back. And that works out to be 0.0373 moles of electrons. So check your math on that. Make sure you know how to use your calculator to get the correct answer. We can now talk about the changes in the cell, the change in mass of the silver electrode. Well, we've got a 1-to-1 ratio between the moles of electrons and moles of silver. So the moles of silver formed would also be 0.0373 moles. And if we want to convert that to mass, we would need to multiply that number by the atomic mass of silver. So 0.0373 moles of silver times 107.9 grams per mole, since it's silver, and that works out to be about 4 grams, a little over 4 grams of silver. At the same time, over here in our zinc compartment, what is happening is the zinc metal is being oxidized to form zinc ion, and we might want to know what is the new concentration of zinc ion after the cell's been running. Well, the moles still have the same number of moles of electrons. The moles of electrons have got to be the same. That's non-negotiable in both half cells. But the moles of zinc will be half the number of moles of electrons. So that would be the moles of zinc ion formed would be 0.0373 over 2, which works out to be 0.0187. And the change in the concentration of zinc ion would be the number of moles per liter, so 0.0187 moles over 0.2 liters. You were told in the beginning that the cell had a volume of 200 milliliters, and that is plus 0.093 moles per liter. The question actually asked for the final concentration, so since the initial concentration was 1 mole per liter, the final concentration would be 1.093 moles per liter. Energy released during this time could be done in many ways, but since we already know how many coulombs of charge are passed, and we know how many joules per coulomb, our cell potential, the energy, I'll use capital Q for energy. Q seems to be the general purpose letter of choice. would be 3,600 coulombs times 1.56 joules per coulomb, and that would be about 5,600 joules, or 5.6 kilojoules of energy. The value for delta G naught, another good chemistry question, is just negative the number of moles transferred times Faraday's constant times the cell potential. I'll go ahead and just not plug this in, but this would be 2 moles of electrons per mole of reaction times 96,500 coulombs per mole times 1.56 coulombs, or negative 301,000, and that's joules per mole of reaction, so you've got to be a little bit careful about your units. A joule and a kilojoule are different things. Not every student seems to be aware of that. So you would normally write that, or typically write that as negative 301 kilojoules per mole. And then I'm going to skip parts J and K because they really deal with a little bit more advanced concepts in terms of what happens in terms of as a cell reaches equilibrium, but perhaps you can work on those on your own. If the cell does reach equilibrium, what's the value of E cell? Well, this equation is actually valid without the standard conditions. Delta G equals negative NFE. Since at equilibrium, one thing you might know is that delta G is 0, and that tells us that our battery is dead, or there is 0 cell potential. And then it's a little bit tricky to calculate the concentrations of each ion when equilibrium has been obtained. Well, actually, the zinc ion is pretty easy because equilibrium, this reaction, the equilibrium constant is going to be so large that this reaction will essentially go to completion, which means that we will use up all of our silver ion, which had an initial concentration of 1 mole per liter. So we will use up half that number, we will produce half that number of moles of zinc ion, and our final concentration of zinc will be about 1.5 moles per liter. And then you can plug that into the equilibrium expression to get the concentration of silver ion. A little bit more advanced, and I don't want to take the time now, since we're looking at the AP exam in about a week, to go over that. If you find an electrochemistry question and you get 7 or 8 out of 10 points, you are doing very, very well. Okay, second question, and this involves a little bit more complicated cell, one that is not just a metal reacting with a non-metal, but the electrochemical principles are the same. And let me try to put this problem on the board for us, and then we can work through it. So a galvanic cell is constructed, and over here we've got a solution of ethanoic acid, or acetic acid, which is HC2H3O2. And we've got a inert but reactive surface, so we've got platinum as my surface of choice for that. And then we have another half cell, and in this half cell we have oxygen and acid. So we've got a strong acid, and we've got some tube that might bubble in oxygen. These are bubbles of O2 gas. And we have another platinum electrode over here. And those electrodes are connected with a voltmeter and a salt bridge. And it's hard to see what's going on, but you are given a table of standard reduction potentials. And I'm going to go ahead and reproduce that over here. So oxygen in acidic solution will gain 4 electrons to become water, and the standard reduction potential there is positive 1.23 volts. And then I'll skip the second one because that's just our basis. That's by definition or by convention taken to be 0 reduction potential. And we have 2 carbon dioxide molecules reacting with 8 hydrogen ions and 8 electrons to form an ethanoic acid molecule. HC2H3O2, and our potential there is minus 0.12 volts. And those are our two half reactions. The first question asks us for the overall reaction that takes place, and pretty clearly we're going to have to flip one of them around, and the one we're going to have to flip around is this one, since our ethanoic acid needs to appear as a reactant. So I'm going to go ahead and write that equation as an oxidation. So we've got HC2H3O2 going to 2 carbon dioxides, 8H plus 8 electrons. So that's the first step in combining these half reactions. And then the second step will be to make sure you can see all this. Okay, I apologize if that was not clear earlier. The second step is going to be to make sure the total number of electrons lost and gained match up. So we've got 4 electrons there and 8 electrons there. So we'll multiply this by 2. And what we will get is 2O2 plus 8H plus 8 electrons plus an ethanoic acid molecule going to 2 times 2 would be 4 H2O plus 2 CO2 plus 8H plus 8 electrons. And now we're going to cancel the electrons, certainly, but also in this case we can cancel 8 hydrogen ions. Any species that appears on both sides of the equation will not change, and we can just omit it. So our overall reaction would be an ethanoic acid molecule plus 2 oxygen molecules, giving us 4 waters and 2 carbon dioxides. The electron flow here, since this ethanoic acid is releasing electrons and oxygen is taking in electrons, the electrons will flow this way, as will the positive ions. The cations will flow that way as well. The cell potential will just be the difference between the two reduction potentials, so 1.23 volts minus negative 0.12 volts is 1.35 volts, or 1.35 joules per coulomb. And the delta G would be negative. In this now we get 8 moles of electrons per mole of reaction times 96,500. Remember that 8 came from the number that we crossed out over here. 8 electrons were lost and gained. Coulombs per mole of electrons times 1.35. I'll write a volt as a joule per coulomb. And now my coulombs cancel and my moles of electrons cancel. And I've got for the final answer here, negative 1040000 joules per mole of reaction, or negative 1,040 kilojoules per mole of reaction, or even negative 1.04 megajoules per mole of reaction. A little bit of a stoichiometry question here. Same thing we did earlier. If we pass 0.2 amps for 5 minutes, I think most of you will remember that the charge is the current times the time. So Q would be our current, 0.2 coulombs per second, times 5 minutes expressed as 300 seconds would be 60 coulombs of charge. Anything we're going to need to do after this, we are probably going to want moles of electrons, so let's go ahead and do that immediately. Moles of electrons would be just 60 coulombs divided by Faraday's constant, 96,500 coulombs per mole, and that works out to be 0.000622 moles of electrons we can relate that stoichiometrically to the moles of ethanoic acid because we have an 8-to-1 ratio. So the moles of ethanoic acid consumed in this time would be 0.000622 moles of electrons times 1 mole of ethanoic acid. Boy, these formulas get a little bit confusing, per 8 moles of electrons. And that works out to be a whopping 7.77 times 10 to the negative 5th moles of HC2H3O2. Good, and finally, you might do this to measure the concentration of ethanoic acid in a solution, in which case the concentration of our solution, H3O2, is just the moles divided by the volume. You were told that the cell had a volume of 100 milliliters. Remember, let's express that as 0.1 liters, and that makes the arithmetic very easy. 7.77 times 10 to the negative 4th moles per liter. Okay. So a little bit of titration data, not quite titration, but analysis data, but fundamentally an electrochemistry question. And then one more question for us. We'll work quickly through this. That also illustrates some electrochemical principles in a little bit less familiar way. We might have a metal air cell, and these are cells that could generate generate power from a spontaneous chemical reaction. All of these galvanic cells are spontaneous. You get work from them, so they have delta G values that are negative. And you've got a picture here, but you've got a cell where we've got a cathode that is porous to oxygen gas and a metal anode and an electrolyte paste in between, and we've got a switch and we can measure a potential here. And you've got a table of reduction potentials. These are not quite standard. These are done at pH 11. So we're not going to, we don't have that little 0 up there, but they are reduction potentials that we will use. Let's say we have an anode that is metallic calcium in a particular cell. Let's write the balanced net ionic equation, and you've got those half reactions. So let's choose the half reaction. I'll write both of them on the board right here for now. So we've got O2 plus 2H2O gaining 4 electrons to become 4 hydroxide ions. And notice that this is a balanced half reaction. It's only a half reaction because it explicitly includes electrons, but it is certainly balanced for both mass and charge. And we've got a reduction potential of plus 0.34 volts. We have the reduction of calcium oxide with water and 2 electrons to form calcium atoms and 2 hydroxide ions, and that gives us negative 2.78 volts, or we're given that value. We've got to combine these 2 half reactions. And remember, we have 2 reductions, and 2 reductions can't both occur. Since calcium is, we're told metallic calcium is a reactant, we're going to flip this one and bring this calcium to the reactant side. We also would generally, for galvanic cells, flip the one with the lower or more negative reduction potential. So let's go ahead and do that. And that gives us calcium atoms plus 2 hydroxide ions. And if you those students who are too tired or don't think the charge on the ions are important, this will get you into big trouble on the AP exam, and you will it's not the sort of thing where if you forget it, you'll lose a point the first time you forget it and then be forgiven after that. Every time you forget to or neglect to put the charge in an ion, you will lose credit. And I think that's probably one of the most dramatic ways to kind of falter. So make sure you understand that the charges are an essential part of the formulas. So on the product side here, we've got calcium oxide and water. Now we've got and of course our 2 electrons. We're going to combine these 2 half reactions. I've got 4 electrons being gained and 2 electrons being lost, so I'll multiply this by 2, and that is going to give me O2 plus 2 H2O plus 4 electrons plus 2 calcium atoms plus 2 hydroxide ions. Those are all of my reactants. Going to 4 hydroxide ions. Oops, did I forget to multiply? I did forget to multiply that by 2. 4 hydroxide ions plus 2 calcium oxide formula units plus 2 water molecules plus 4 electrons. And now we can cross off things that show up on both sides. Electrons better show up on both sides, and that was the whole reason for multiplying through. But we also now have 4 hydroxide ions there and there, and 2 water molecules there and there. So our overall equation is 2 calcium atoms plus 1 oxygen molecule forming 2 calcium oxides. E cell and delta G, and these are non-standard, but the E cell would be the difference between those 2 values. So E cell would be 0.34 volts minus negative 2.78 volts, and that is going to be positive 3.12 volts, or joules per coulomb. And delta G, I'll just put the formula up here, delta G would be negative 4 moles of electrons per mole of reaction times Faraday's constant times our 3.12 joules per coulomb. And if you'll work that out as we did earlier, that's about negative 1,200,000 joules per mole of reaction, or negative 1,200 kilojoules per mole of reaction, or negative 1.2 megajoules per mole of reaction. As usual, there's a stoichiometry component here. This time it's a little bit reversed because you're not given the charge, you're given the amount of reactant that has to calculate the charge. So let's say you have a cell here that's constructed with 1 gram, not very much, of metallic calcium, and we pass a current of 0.2 amps. How much time can we pass that current for? And as you know now, the whole trick is going from coulombs to moles, or in this case, moles to coulombs. Let's calculate our moles of calcium. Our moles of metallic calcium would be our 1 gram divided by the atomic mass of calcium, 40.1 grams per mole, gives us 0.0250 moles of calcium. We really want moles of electrons, and since the calcium atoms each lose 2 electrons, the moles of electrons would be our 0.0250 moles of calcium times 2 moles of electrons for every 1 mole of calcium, and that works out to be 0.0500 moles of electrons. Since we're ultimately going toward current and time, we should express this in terms of coulombs. So the charge in coulombs would be our 0.050 moles of electrons, this time multiplying by Faraday's constant, coulombs per mole of electrons, and those will cancel. And when we do that, we get a number of 4,800, rounding to 2 sig figs, coulomb. And remember, Q equals current times elapsed time. We know the current here is 0.2 coulombs per second, so our elapsed time would be 4,800 coulombs divided by 0.2 coulombs per second, And that works out to 24,000 seconds, or about 6 hours and 40 minutes, 6.67 hours. So pretty nice. That one gram of calcium, not even the mass of a paperclip of calcium, could pass a fairly significant current of 0.2 amps for almost 7 hours. And that's why batteries can be really small and last a long time. Okay, a couple of qualitative, well, not a qualitative question, so we're getting to the end here, at least for me. Why does the total mass of the cell increase? Well, we're all used to conservation of mass, and we know that the total mass of the reactants equals the total mass of the products, certainly if you do your stoichiometric calculations correctly. But remember, this is not a closed system, and as the cell operates, oxygen is diffusing in through that porous membrane. Getting back to the overall cell reaction that you wrote, remember that calcium plus O2 goes to 2CaO. So we're adding oxygen gas to our system. Calcium metal and calcium oxide would both be solids, but as we add oxygen gas to our system, it would increase the total mass of the cell would increase. Now, if that cell were in a bigger container that had oxygen gas in it, the total mass of the container would certainly stay the same. What would the increase in mass be? And I think you all know how to do this now. We already have the moles of electrons. Since the half reaction involving oxygen was a 4-electron transfer, the moles of oxygen will be our 0.050 moles of electrons times 1 mole of oxygen for every 4 moles of electrons, and that works out to be 0.0125 moles of oxygen gas is added. To get the mass of oxygen, you would certainly just multiply this number by the formula mass for oxygen, 32 grams per mole, and that gives you an increase of 0.40 grams. And then what happens, a little bit more thermodynamics, what happens if we run this in pure oxygen instead of air, since air, most of you probably know, is about 20% oxygen. Would that time that we calculated, that 6.67 hours, change? And the answer is no, because having it in pure oxygen, we would still be limited by the number of coulombs of charge available from our 1 gram of calcium. But the cell potential would change because we're no longer, well, we're now back at thermodynamic conditions. Remember, E cell equals E naught minus RT over NF times the ln of Q, where Q is this Q. We've got lots of Q's here. This Q is the reaction quotient. In this particular case, Q would be the concentration of products. Well, there's only one product, and it's a solid, so it doesn't change. It's just 1 over the concentration of our reactants. We've got a solid here, and we've got a gas, so this would be we conventionally use the partial pressure of oxygen. If we increase the partial pressure of oxygen, if this becomes bigger, then Q becomes smaller. If Q becomes smaller, then ln Q becomes smaller, since natural log is a monotonically increasing function, and we're going to subtract a smaller value from this, which will increase the cell potential. That's kind of a very mathematical way of looking at it. We might also say that, hey, look at this equation. Increase in the concentration or the partial pressure of a gaseous reactant will thermodynamically decrease the delta G value for the same reasons and push this reaction to the right. It's not quite a Le Chatelier's principle argument, but it's pretty darn close since we're not at equilibrium. Okay, well that's all I have for electrochemistry and galvanic cells. I hope it's useful, and good luck on your AP Chem exams. Bye-bye now.